Hey, and welcome back. So we're going to look at the integrated rate law for a first order reaction. And so remember, all we're trying to do is figure out how concentration changes with time. And a first order reaction is one where it's got a rate law that looks something like this. And we are going to be looking at a reaction A goes to products, let's say. So we can go ahead and we can solve this using a little bit of calculus. And we can show that the rate of the reaction is equal to, let's see, the change in concentration of A with time. So we're just using our definition for what we mean by reaction rate, and it's equal to K times by A. So this is actually what we call a differential equation, and we can use a little bit of calculus. We can essentially integrate it, and when we integrate it, what we find is that we get the natural logarithm of the concentration at time t is equal to minus the rate constant times the time plus the natural logarithm of the concentration at the beginning of the experiment. So the little subscripts there are telling us at time t and at time 0, so the start of the experiment. So that is time, and that is the rate constant. So ln, of course, is the natural logarithm. So we call it an integrated rate law because essentially we just integrate this to get this. And, we won't assume you've got a calculus, so we'll just go ahead and leave it like that. We can also rearrange this equation as well, so we can use properties of logarithms. We know that the logarithm of one thing minus the logarithm of a second thing is equal to the logarithm of the first thing divided by the second thing. So that allows us to take this expression here. You can imagine subtracting this from both sides. So in essence, what you have is now the log of that minus the log of that. And we can make use of the fact that when you've got the log of one thing minus another, it's the same thing as the log of the things divided by one another. So we can go ahead and rewrite that. So now that's the log of the concentration at time t over the original concentration. Okay, and that's equal to minus kt. So you can use whichever expression you prefer. They're both identical. So maybe you just prefer to use one, maybe you prefer to use the other, whatever floats your boat. So let's look at an example problem. So maybe we've got a first order reaction. So we always have to know if it's first order because the equations that we're going to develop depend upon the order. And we've got a rate constant is 0.038 seconds to the minus 1. And we've got an initial concentration of A of, say, 1.5 molar. And the question is, how long does it take, so T question mark, for the concentration to drop to 0.15 moles per liter. So we've got some kind of reaction A going to form products, so we're keeping this pretty generic. We know that the concentration of A will drop over time, and so we're going to have, actually it's going to be an exponential decay, we'll talk about that later. And we're starting out with 1.5 moles per liter, and we're ending up at 1/10 of that, so 0.15 moles per liter. So the question is, what time does that occur at? So we can immediately start by writing down our integrated rate law. So a couple of different ways to do it. We can start with the final one, I guess. So the log of the concentration at time t over the original concentration is equal to minus k times by t. And those will always be given to you on an exam, by the way. And we can just kind of check what we have here. So we've got these concentrations, we've got the rate constant, right? So we're trying to solve for t. So we can do a little bit of algebra, and we can immediately solve for t. So t is equal to, let me see, the log of A at time over A at the start divided by minus the rate constant. So at this point here, we can really just kind of plug stuff in. So I'm going to go ahead and start plugging things in. So we've got the log of the concentration at time t, so that is our 0.15 moles per liter, over the log of our original concentration, that's 1.5 moles per liter, so that's the log of essentially 1/10, divided by minus the rate constant, so that is minus 0.038 seconds to the minus 1. And if we go ahead and we calculate the log term on the top, we get a negative number, and so actually that whole thing is negative, and there's a negative, so we get a positive time, which is encouraging. And if we plug this in our calculator, we get to two significant figures, 61. And in terms of the units, so the top doesn't have any units, the bottom's got units of seconds to the minus 1. So since we're inverting it, it's becoming seconds. So essentially it's going to be 61 seconds, or it takes about a minute for this reaction to occur.